What even is electricity? I want to start to explain that with kind of a metaphor, an analogy. So I've got a hill. On top of this hill, there is a ball. Okay, so in terms of energy, this ball has some energy. It's got some energy because it's able to roll down. So there is energy present. It's concentrated in this object, and the way that it can be released, the way that energy can spread out as the second law of thermodynamics requires, is that the ball can roll down. If the ball rolls down, then energy can spread. And really, when I say that energy can spread, I mean that this concentrated energy can lower as this rolls down. So when we're conceptualizing this ball rolling down, we know that there is a force that's causing that to happen. And that the force is present on the ball, whether it's at the top of the hill or the bottom. It's just that once it reaches the bottom, it can't go any further. And so it stops at the ground. Okay, so we have here a heightened energy state and then a neutral energy state. Energy is present and concentrated in the form of gravitational potential energy, and energy tends to spread out. So instead of being concentrated here, it will not be concentrated, and the energy will end up being dispersed through there. So just because there's a ball on a hill doesn't mean it's going to roll down. It might be stuck. It's going to have to overcome some sort of resistance to actually moving. So I'll put down that you must overcome some resistance. And it's worth noting that there will be friction all the way down the hill, which means that some energy will be spent overcoming that resistance. Okay, so the right side of this, energy present can spread, caused by force, stops at ground, must overcome resistance, and energy spent, is descriptive of the ball on the hill, but it is also descriptive of electricity. So let me redo this drawing, but from the point of view of electricity. So there must be some energy present, but its source is not going to be gravitational. There has to be some sort of electrical energy. Now, atoms are made of electrically charged particles, which means that you can get electrical energy by arrangements of atoms. I'll go into detail about that a little later, but let me just go ahead and have some energy in the form of a battery. So I'm going to go ahead, draw a battery. I'm going to draw like a AA battery. There we go. So I've got a battery here, and there is energy present in that there is an energy difference between this side and that side. Now, in the case of the hill, I had an uphill and a downhill. if I'm going to have an energy difference, I need to be able to conceive of one of these as the uphill and the other one as the downhill. Let's treat this as if it's the top of the hill, and this as if it were the bottom of the hill. In order to get from the top of the hill to the bottom, they needed to be connected. And they needed to be connected by something that the ball could actually travel on. So what's going to be traveling here? Not a ball rolling down a hill, but electrons flowing through some sort of conductor. Metal is a good electrical conductor, so I'm going to connect the positive side of this battery to the negative side. There is now a path through which the high concentration of energy can spread out and go to where the concentration is lower. Okay, so I got energy present in the form of the battery. It can spread by moving through the wire. It's caused by a force. So in terms of the hill, I've got the force of gravity, which is basically causing the ball to roll down. If you could kind of imagine yourself as the ball, it makes you, want to roll down. So what's causing the electrons to want to move? There is a quantity which describes the urgency with which the electrons move, and that is called voltage. And if you needed a quick and easy way to remember what voltage is, I would recommend that you remember it as electrical pressure. Pressure in quotes, because obviously it's not actually pressure, but I'm calling it pressure because it is what gives the electrons the urgency to move. Higher voltage means the electrons are being, pushed harder. Okay, so the energy is present in the form of a battery. It can spread by traveling through the wire. It's caused by a force, and we just describe the force that makes the energy spread out as gravity. I will describe the impetus for the electrons to pass from high energy to low energy as voltage. Stops at ground. Well, once the electrons from the high concentration end up in the place with the low concentration of energy, we actually call that ground. That's what it's called in an electrical circuit. Maybe you've heard of an electrical ground or maybe a ground wire. Ground in this case just refers to where the energy gets dumped when it's spreading out. It's not too different from this. The energy gets spread out when the ball ends up on the ground. You can't go lower than the ground. Similarly, energy is in high concentration here and in low concentration here. Once the energy ends up in the low concentration, it can't get any lower. So we would call that a ground. Must overcome resistance. So in order to get electricity to flow through this wire, you need to give enough energy to each metal atom to be able to lose an electron, to pass it along. That is a low cost for an electrical conductor, but it is not a zero cost, which means that it's going to cost this battery some energy just to get the electrons moving around. Like I said, a good conductor, it won't cost very much, but for a poor conductor, it should cost a lot. And that will cost you some energy. Now, if you've used anything with a battery in it, you know that eventually that battery dies, which means that that energy is being used up somehow. Now, what a waste it would be if all that's happening with the energy is the battery is just being killed by letting the energy concentration spread out. What use would you have for concentrating a whole bunch of energy in one side of the battery and letting it spread to the other side? Well, let's go back to the other example. What use could you possibly have for having a ball on top of a hill? Any reason at all? I mean, this one is a little strange. So maybe you can think of a different scenario being more useful. How about if instead of a hill with a ball on it, we had a longer, much more gradual hill? And it had some water on it. Wouldn't you be able to construct a dam, take advantage of the fact that this water is slightly uphill of this water, that this water is being urged by gravity to flow downhill? And if you stick an obstacle in the way, there's enough energy here to push through the obstacle, but some of that water's energy will be lost in that push, and we can capture it with a turbine and get hydroelectric power. Well, I mean, I guess you could do something like that if you put like some sort of mill wheel on the hill so that when the ball rolled down it would spin the wheel, but that's a bit unrealistic. Well, let's go back here. So we've got a battery. It's just connected one end to the other with a wire, and there's really no energy cost for the electricity to go through here. This is called a short circuit, in which it's just a wire connecting the two ends of the battery. Short circuits are typically bad, and it's because the transfer of energy would be so intense it would probably cause this wire to heat up substantially. Might even make that battery heat up so much the acid in it would boil and the battery would explode. So yeah, let's not actually have this happen. Let's put a dam in the stream. So instead of letting this wire just be a bare wire, I'm going to stick something on here, okay? I'm going to I'm going to draw it with a zigzag line to kind of like make it resemble how it's now a difficult road. So this thing is called a resistor. I'm going to label it R. And what that does is it has a higher cost of energy for the electrons to pass through it. And that means that it's going to spend some of the energy that's spreading out just to get past it. Now, depending on how that energy is spent, it's going to make this resistor have some different uses. So maybe we can think of a couple different things that electrical energy might be useful for. So let's see. If the energy is spent, energy doesn't just disappear. It has to be converted. So if the electrical energy is spent and it's converted into heat, well, you might just have yourself an electrical heater here. If you pass electricity through a resistor, and in order to get through the resistor, the energy is spent in that it is spread out through the atoms of this resistor, you could have a stovetop, an electric heater, anything that produces heat. Okay. Maybe instead of producing electromagnetic radiation in the infrared range, maybe it produces it in the visible range. Well, it may also be that it's so hot that it's glowing, or it could be that the substance is chosen such that it only emits light in the visible range. That would be something like an LED, but a typical incandescent light bulb from way back when, they do produce a lot of heat, but they also do produce light. Okay, well, there are other ways that that energy can be converted. If instead of using a resistor, you made it go through a coil of wire, you might actually cause magnetism. And because of the properties of magnetism, you could also get movement out of that. This is just the surface because, as I'm sure you know, electrical devices are incredibly, infinitely useful. And by a very clever arrangement of a circuit, you can make it do almost anything. But we're just trying to learn what electricity is in general. So, to sum up, electricity is best understood the same way all these other systems in physics are understood. Understand it from the point of view of energy. There are all kinds of energy, gravitational energy, thermal energy, but we're talking about electrical energy. Electrical energy is present within the particles that make up atoms. Protons are just positively charged. Electrons are just negatively charged. Atoms are neutral because they contain the same number of both of them. However, the energy is present. And you can have a concentration of electrical energy either by arranging the charged particles in atoms in certain ways or by stockpiling them, having a whole bunch of extra electrons in one place. That's one way that you can have electrical energy be present. Once the electrical energy is concentrated, it needs some avenue through which to spread out, just like this ball needs to roll down the hill or this water needs to flow downhill. We describe the urgency with which this energy spreads out as a force. In the case of the hill and the water, we would call that gravity, but if it's a circuit, we could describe that as voltage. At some point when the energy is fully spread, it will stop. We call that place the ground, whether it is something falling or electricity. It must overcome resistance. Depending on the nature of the avenue by which the energy spreads, some energy is going to be spent either overcoming friction or spinning a turbine or heating up the metal that the electricity is traveling through, and that does cost some energy. Okay, there is only one other difference between electricity and gravity that really needs to be mentioned in order to make sense of this, and that is that gravity reaches the ground and then it's done. There's no negative elevation. When it comes to electricity, there is a neutral, and you could be above ground or you could be below ground. There is a negative and a positive for electricity. There is no negative for gravity. Gravity just goes down and it will never come back up. You could have an overabundance of electrons or a whole bunch of electrons missing. Either way, you have a concentration of electrical energy, and that would seek to be equalized in the same manner. Anyway, that is what electricity is. After this, we would just need to talk about the specifics of how we describe in physics the flow of electricity and talk about some specific kinds of behaviors you could see from circuits.